Okay, so your next topic, that is molecular orbital theory, and the molecular orbital theory, in short, it is represented as MOT. Okay, and this theory, which is given by Hunt and Mulliken. Okay, mainly this theory is used to describe the configuration of a diatomic molecule, or used to describe the property of a diatomic molecule. In terms of what? We know that valence bond theory, which describes the nature and whole idea about a polyatomic molecule in terms of quantum mechanical model, like that. This theory is used to explain the properties of diatomic molecule in terms of quantum mechanical idea. Okay, fine. So it's given by Hunt and Mulliken. So first, there are some postulates or features of this theory. So you copy that. First one. Electrons in atom are arranged in atomic orbital. We all know that. Electrons in atom are occupied in atomic orbital, whereas electron in molecules are similarly, they are occupied in molecular orbital. Okay, electron in atoms occupied in atomic orbital, likely electron in molecule occupied in molecular orbital. Okay, so that's the first postulate. Second postulate, we know that, don't write. Okay, we know that atoms are combined to form what? Molecule. So when atoms combine to form a molecule, the atomic orbitals of atoms also combined to form the molecular orbital. So the next point, molecular orbitals are formed by the linear combination of atomic orbitals. Okay. Next point. Unlike hybridization, here the orbital to be combined should have same energy, same shape. Okay. 1s orbital can combine with the 1s. 1s orbital of one atom can combine with the 1s orbital of another. 2s orbital of one atom can combine with the 2s orbital of another, like that. Okay. But in case of hybridization, S can mix with the P and also can mix with the D. Okay. But unlike your hybridization, here the linear combining orbitals should be should have same energy and orbitals. So the next point, the combining orbitals should have same energy and same shape. Okay. Next, like your hybridization, how much orbitals combined, that much how much atomic orbitals combined, that much hybrid orbitals formed in your hybridization, like that. How much atomic orbitals combined, that much molecular orbital formed here also. Okay, so number of atomic orbitals combined is equal to number of molecular orbitals formed. Number of atomic orbitals combined is equal to number of molecular orbital formed. Okay, ready? Fine. Next point, atomic orbital is monocentric. Because atomic orbital is the probability of, region where the probability of finding electron in an atom maximum, where atoms all have a single nucleus. Whereas molecular orbital means that is also a region where the probability of finding electron is maximum, but molecule having more than one atom, so more than one nucleus. So a molecular orbital is orbital which found in molecule, where the molecule have more than one nucleus, so molecules are polycentric. So that is a next point. Atomic orbitals are monocentric, but molecular orbitals are polycentric. Okay. Next point, if the combination of atomic orbital along internuclear axis, sigma molecular orbitals formed. Like your overlapping of atomic orbital. If the overlapping of atomic orbital is along internuclear axis, there forms, and we know end-to-end overlap, there forms sigma bond, like that. Here forms sigma molecular orbital. If the overlapping of orbital perpendicular to internuclear axis, next the very same point, if the overlapping of orbital along internuclear axis, which means along Z axis, then there forms sigma molecular orbitals. Or if the overlapping of orbital perpendicular to internuclear axis, then there forms pi molecular orbitals. Okay, fine. So these all are the main postulates. Ready? So the next concept, that is LCAO. LCAO, linear combination of atomic orbital. Okay, let psi A is the atomic orbital. Psi A is the atomic orbital. And psi B is the atomic orbital of atom A. Atomic orbital of atom A. And psi B is the atomic orbital of atom B. Psi B is the atomic orbital of atom B. Okay. Then consider the linear combination. LCAO. Consider the linear combination. And what about the linear combination of this atomic orbital means? When we know that atomic orbitals are represented by a wave function like this. So this psi A represents this wave and psi B represents this wave. Okay. Let its amplitude be a lower one. This is psi B and this is psi A. Okay. So when the two atomic orbitals combined means the two waves are combined. The combination of two waves are said to be interference, right? Right. I think you are familiar with that in physics. Okay. So there are two chances when psi A and psi B waves are in same phase. When psi A and psi B waves are in same phase, when they are in same phase. Okay. When they are in same phase, the phase difference is 0. Okay. Then they undergoes constructive interference. Then they undergoes constructive interference. So due to that constructive interference, what is the speciality means? The wave functions get added. That means a net wave with a high amplitude formed, and this wave is having an amplitude of psi A plus psi B, and this represents a orbital. Psi A represents a orbital atomic orbital A, psi B represents a orbital atomic orbital B. So psi A plus psi B also represent a orbital, and that orbital is said to be, and the orbital which is formed by the additive combination of two wave function due to constructive interference, and that orbital is said to be bonding molecular orbital BMO. Okay, like that. There is one more chance. If psi A and psi B are in opposite phase, then they constitute a destructive interference. They forms a destructive interference. And the destructive interference where the amplitude will be psi A minus psi B, and let the corresponding wave I can represent as a small wave, and the amplitude is the difference between amplitude of psi A and psi B, whatever it may be. This also a wave. So this also a wave with an amplitude of psi A minus psi B. So this also represents an orbital, and that typical orbital is said to be antibonding molecular orbital. So if we have two atomic orbitals psi A and psi B, there are two chances for combination. Either the additive combination, that means when the two waves are in same phase, forms a constructive interference to form additive combination, and there forms a bonding molecular orbital. Or if it is a destructive interference when the phase difference is 180 degree, or where they are in opposing phase, then there forms a wave with the difference of this amplitude, and that represents the antibonding molecular orbital. So generally, it is clear that when there are two wave functions or two orbitals are combined, there will be a chance for additive and subtractive combination. Additive and subtractive combination. And this combination is said to be linear combination of atomic orbital. So due to additive combination or subtractive combination, there forms Psi A minus Psi B. Due to additive combination, there forms Psi A plus Psi B. And the Psi A minus Psi B, Psi A plus Psi B. Psi A plus Psi B is said to be bonding molecular orbital. Psi A minus Psi B is said to be anti-bonding molecular orbital. So this is said to be the linear combination of atomic orbital. Okay, fine. So now you realize why the two, when the two are combined, the forms additive and subtractive combination. It is due to the constructive and destructive interference. Fine, enough. And what is a speciality means? If you consider the energy barrier here, if this is the energy of energy of A and B, then antibonding molecular orbital have more energy than what? More energy than the ABMO have more energy than the individual Psi A and Psi B. This is the energy of Psi A and Psi B. And what about the energy of antibonding molecular orbital means? That is much greater than individual orbitals. So they are relatively less stable. Since the potential energy is higher, antibonding molecular orbitals are relatively less stable. Okay. What about here? Here, what happened means Psi A plus Psi B, fine. This is additive combination to form the molecular orbital, where the energy is comparatively less than the energy of each orbitals. Okay, so less energy than Psi A and Psi B, less energy than Psi A and Psi B. So therefore, more stable. So greater the stability for your bonding molecular orbital. Okay, fine. So this is a concept of. So it is very clear that when there are two atomic orbitals, Psi A and Psi B, when they are combined, they forms two molecular orbital. One is by additive combination with the low energy, another is by subtractive combination with high energy. Physically, the meaning is one is by constructive interference, another one is by destructive interference. Okay, fine. So now let me introduce the electronic molecular orbitals. Okay, followed by order for electronic configuration. Then some examples. Okay, so we require 1 to 20 electrons here. Okay, we have to configure only 1 to 20 electron. So I'll give you the order for that 1 to 20 electron. Before that, I am introducing the molecular orbitals. Okay, if oneness of one molecular orbital combined with the oneness of another molecular orbital. Okay, so if psi oneness combined with the another psi oneness, another atom of atomic orbital of another oneness, then there forms what? There is a additive combination psi oneness plus, or there is a subtractive combination psi oneness minus psi oneness, additive combination psi oneness plus psi oneness. Okay, so this is the bonding of oneness and this is the antibonding of oneness. Since the combination of two s orbital is always along internuclear axis, the formed molecular orbital having an initial of sigma. So the bonding molecular orbital by the combination of oneness orbital of two atoms, that leads to sigma oneness. Sigma, now you know, oneness stands for the molecular orbital from oneness or combination by oneness orbital, and the sigma that represents what? Sigma that simply represents the combination along internuclear axis. Okay, like that. If this is the antibonding molecular orbital from oneness and oneness, then this is also oneness, but the antibonding moleculars are usually represented by a star on the top. Okay, like that. What about the 2s? 2s plus or minus psi 2s. Okay, fine. So tell me, Tell me the case. There is also two chances, psi 2s plus psi 2s, which leads to the molecular orbital of 2s, which will be sigma 2s. Here, the subtractive combination of psi 2s minus psi 2s, which leads to the sigma star 2s. Okay, ready. Like that, we have three p orbitals. Let the consider the combination of 2pz with another 2pz. We know the 2pz combination will be along internuclear axis, so the formed orbital is again sigma orbital. Okay, where the sigma 2pz by subtract additive combination, and sigma star 2pz by the subtractive combination. Like that, the next wave function is 2px, the combination, linear combination of 2px's. Okay, but we know that x orbital is perpendicular to internuclear axis, therefore the combination leads to the formation of pi molecular orbitals. So there forms the additive combination to form pi 2px and subtractive combination to form the pi star 2px. Okay, similarly one more, the combination between two py orbitals. Okay, two py orbitals. Ready. So here the additive combination to form pi 2px, pi 2py, and subtractive combination to form pi star 2py. So these all are the different molecular orbitals for configuring electrons, from the electrons from 1 to 20. Okay, so you have to know the order for 1 to 20. Okay, for 1 to 20, the order is, listen, sigma 1s less than sigma star 1s less than sigma 2s. This is the an energy order, or this is based on, this is the Aufbau principle order. Sigma 1s less than sigma star 1s less than sigma 2s less than sigma star 2s less than sigma 2pz less than pi 2px equal to pi 2py less than pi star 2px equal to pi star 2py less than sigma star 2pz. So I already introduced this all orbitals. Now this is the order of electronic configuration, or this is the order for configuring the electrons using Aufbau principle. Okay, fine. Ready. So this is based on orbital, or this is the energy of molecular orbital, energy order of molecular orbital. Okay, and this electronic configuration also obeys Aufbau principle, Hund's rule, and the rules that all which are obeyed in your atomic orbital configuration. That means it obeys Aufbau principle, Hund's rule, and Pauli subscription principle. Okay, fine. But there is an exception. There is an exception. For elements like B2, C2, N2, which means electrons like 10 electron, B2. Boron have 5 electron, so B2 10 electron. Carbon have 6 electron, C2 12 electron. Nitrogen have 7 electron, C2 N2 14 electron. Okay. So for this category, they are 2s and 2p energy comparatively low. The energy difference between the 2s and 2p of these two orbitals are comparatively low. Since they are comparatively low, they undergoes mixing, and that phenomenon is called 2s2p mixing. Due to that 2s2p mixing, there is a small difference in energy order. There is a small difference in energy order for these species only. That means here is the difference. Here is the difference. This gets shuffled. So what will be the order? So no need to find the whole order. What will be the order? This gets shuffled only for these elements. Okay, what about the order? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This much there is no problem. Followed by, due to 2s2p mixing, the energy order for this one are different. So followed by the pi, then the sigma. Pi 2px, pi 2py less than sigma 2pz less than pi star 2px. The remaining is same. Pi star 2py, sigma star 2pz. Okay, fine. So this is the case. Ready? So now let me discuss the application of this one. Okay, well, the star represents the antibonding electron, and orbital without star represents the bonding electron. And this is also orbital, so it can accommodate a maximum of 2 electrons. Okay, and this is also based on Ncert polysaccharidation principle and everything. Okay, so now some applications are there based on configuration application. Okay, if Nb is the number of bonding electron, which means electron in bonding molecular orbital. Na is the number of antibonding electron, which means electron in antibonding orbital. Then bond order is equal to half the difference between bonding electron and antibonding electron. So you simply write the configuration and find the bond order and find the number of bonding electron and antibonding electron and make the half of that. Then you obtain what? The bond order. Okay. If we know the bond order, we can arrange them in bond length and bond energy. If we know the bond order of some species, then we know that the bond order, exactly the same order follows for bond energy, but the reverse order follows for bond length. Okay, so if you know the bond order of a different species using molecular orbital configuration, then you can easily arrange them in bond energy order or bond length order. Okay, you know what is bond energy, bond length? We already discussed that in bond parameters. Number 3, in order to find the stability, we can define the stability. Okay, if the bond order of a species, I'm sorry, this is not NB. If the bond order of species positive, how the bond order become positive? If your NB electron greater than Na, then the molecule stable. Else, if it is negative or 0, else. Otherwise, if it is not positive, then the molecule unstable. Okay. In the next application, we can easily predict the magnetic property. We can predict the magnetic property, and you know, based on magnetic property, we can the main classification is paramagnetic and diamagnetic. So magnetic property also described by this one. Okay. So listen. If any orbital have unpaired electron, what happen? Paramagnetic. Then it is paramagnetic. Okay. If all orbital paired, then that is said to be diamagnetic. Then the molecule is known as diamagnetic. Okay. So the next we can discuss some examples. So normal examples, H2 only 2 electron, because hydrogen have 1, so H2 2 electron. So the electronic configuration sigma 1s2 less than sigma star 1s0. There is no electron for your antibonding molecular orbital of 1s. So this is NB equal to so NB equal to 2, Na equal to 0. So the bond order is 2 minus 0 by 2. So that's equal 1. So the bond order of hydrogen is 1. That we already know that hydrogen where the number of bond is 1. Okay. So moving to the next example. The next example, that is hydrogen followed by He2. There are actually 4 electrons. Okay. So if there is 4 electrons, what happens? Sigma 1s2 less than sigma star 1s2. So number of bonding equal to number of anti-bonding equal to. So bond order is equal to 2 minus 2 divided by, and this having one bond order. So bond order positive, so the molecule is stable and all orbitals are paired in hydrogen. So this is diamagnetic. Okay, here that is 2, yes 2, answer is 0. So this is unstable. He2 is unstable since the bond order is 0. And there is no molecule like that. So no need to discuss the magnetic property of that molecule, okay, because the molecule is unstable. The next example is Li2. Li2, there will be 6 electron. If there is 6 electron, the configuration is sigma 1s2 less than sigma star 1s2 less than sigma 2s2. Okay, so the bonding electrons, these are bonding orbitals. So bonding electron 6, anti-bonding electron, that's 2. So the bond order is 6 minus 2 by 2, that is this is not 2, this is not 6, this is 4, I think. 4 minus 2 by 2, the bond order is 1. So the molecule is stable since the bond order 1 and all orbitals are paired, and this is diamagnetic. Okay, consider the next example, that is Be2. Okay, there are 8 electrons because beryllium have 4 electrons. So configuration is sigma 1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2. Okay, so bonding electron and anti-bonding electrons are same, and that is equal to 4, right? 2 orbital bonding, 2 orbital anti-bonding. So the bond order is 0. 4 minus 4 divided by 2, that's answer is 0. Since the bond order is 0, the molecule is unstable. Okay. Now the next important example, B2 have 2s2p mixing. 2s2p mixing. So the modified order is the case. Okay, fine. So there are actually 10 electrons. So sigma 1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2. Fine. In the case of modified order, what happens? The next category, that is pi. So the next is pi 2px equal pi 2py, right? Pi 2px equal pi 2py. Listen, if pi 2px equal pi 2py, we already arranged 8 electrons here. So we have 2 more electrons. But this follows Hund's rule. So it is clear that these 2 orbitals have same energy, which means these 2 orbitals are degenerate. So you want, or you are not permitted to fill 2 electrons here, the next 2 electron, because totally 10 electron, 8 is here, the next 2. You can't configure it like this because it violates Hund's rule. Because these 2 orbitals are what? These 2 orbitals are what the hell? These 2 orbitals are having degenerate, so you are not permitted to pair here. Ready? Fine. So you have to configure this in like this. First electron for the first, second for the next. If there is a third electron, you can pair here, because if the degenerate orbital is half filled, you can pair the first one. So this is the molecule. Okay. For the total number of bonding electron is 2, 2, this together forms 2, 6. Antibonding electron is 4. So bond order is 6 minus 4 by 2. That's equal 1. Okay. And the main property, that is 2 orbitals are unpaired, the molecule is paramagnetic. Paramagnetic. Okay, fine. So let me modify the configuration of next here itself. Okay, fine. Listen. The next molecule is C2. Okay, C2. Have 12 electron. And there is 2s2p mixing, you know. So the order is like this. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. 8 electrons are over. Then we have 4 more electrons. So you have to supply 2 electron here, 2 electron here. Because there is 4 electron actually. Okay. Fine. What is the bond order? What is that bond order? Tell me. Bond order is equal to number of bonding electron 1, 2, 3, 4. 8 bond order is 8 minus 40 odd by 2. So bond order is 2. So this carbon have a bond order of 2, and exceptionally these 2 bonds are pi bond. This is an exception. These 2 bonds are pi bond because the 2 bonds are formed by the overlapping of these pi orbitals. So these 2 bonds are pi bonds. Okay, and this is important. Sometimes they may ask like that. The bond order of carbon C2, where the 2 bonds are pi bond. Usually if there is a double bond, then one is single, then another one is double. Here the 2 bonds are pi bond. Okay. What about the next? The next molecule, that is nitrogen. So nitrogen N2, electrons with 14 electron configuration, and they have 2s2p mixing. So sigma 1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2. Okay, sometimes this represented like this, Kk. Kk means the first shell is filled. Okay, so instead of this they may write like this also. Followed by what? Followed by this having 2s2p mixing. So pi 2px equal pi 2py, where here is 2 electron, 2 electron, more than 2 more electron there, which goes to the 2pz. Okay, so the bonding number of electron, that's actually 1, 2, 3, 4, 5. 10 bonding electrons, 4 anti-bonding electrons, where the bond order is 10 minus 40 odd by 2, that's equal 3. And we all know that in case of nitrogen, the bond order is 3. Okay, fine. And weight. And this species is diamagnetic, right? Because all of orbitals are paired. The next is O2. O2 with 16 electron. There is no 2s2p mixing. So as usual order. So sigma 1s2 less than sigma star 1s2 less than sigma 2s2 less than sigma star 2s2 less than. If there is no 2s2p mixing, pi 2pz2 less than sigma 2pz2 less than pi 2px2 equal to pi 2py2. And there is actually 2 more electrons which goes to the pi star orbital of oxygen. Pi star 2px1 equal pi star 2py1. This is a configuration of oxygen, where the number of bonding electron, you can count it as 2, 4, 6, 10. 10 is bonding, then the remaining 6 will be anti-bonding. Bond order is 10 minus 6 by 2. That's equal to, we all know that oxygen have double bond. And this is ultimately paramagnetic. The paramagnetic property of oxygen can be explained on the basis of 2 unpaired electron in the pi star orbital. Okay, And if you can write the, and what about the configuration of F2? Okay, and no need to spend that more time. If the molecule is F2, what happens? 18 electron. There is no 2s2p mixing, so additionally 2 electrons will be here. Okay, so this will be 8, so bond will be 1. Okay, so there is FF single bond. Ready? And if it is Ne2, or this F2 will be diamagnetic because there is all electrons are paired. If it is Ne2, what happens? 20 electron. 20 electron means the next orbital, that is sigma star 2pz2 also filled. So number of bonding equal to number of anti-bonding, 10, 10. So bond order will be 0, unstable. Okay. So wait, one more idea. Let's write the configuration of H2 plus. H2 plus, the electron actually only one electron. So if there is an odd electron, if there is an odd electron, what happens? The orbital will always unpaired. If there is odd electron, the orbital is always unpaired. Okay, keep it in mind. Now, always unpaired means the molecule is always paramagnetic. Now, I'll give you some tricks for this. Number of electron, bond order. You can easily predict the bond order based on number of electron. If the number of electron is 8, actually there is a controversial order which exactly present after 8 electron, right? Sigma 1s2, sigma 2s2, sigma star 2s, sigma 1s2, sigma star 1s, sigma 2s, sigma star 2s. Up to that much, which means up to 8 electron, there is no problem. After 8 electron, the 2s2p mixing is operative, right? So there you may have the confusion. So no need to write the electronic configuration actually. You can easily predict the bond order base if you know the electrons. Okay, if 8 electron, the bond order is 0. If 9 electron, the bond order is 0.5. If 10 electron, the bond order is 1. If 11 electron, the bond order is 1.5. If 12 electron, the bond order is 2. It is clear. Your carbon have bond order true, right? And your boron have bond order 1. Okay. If 13 electron, the bond order is 2.5. If 14 electron, the bond order is 3. Okay. Now it get decreased. It get decreased. If 15 electron, the bond order again 2.5, decreased. 16 electron 2. 17 electron 1.5. 18 electron, that's 1. Your fluorine have bond order 1, oxygen have bond order 2. That's perfect. 19 electron, bond order 0.5. 20 electron, bond order 0. So this is an idea, okay? And we all know that all odd electron species are what? All odd electron species are okay. All odd electron species are diamagnetic, right? Sorry, all odd electron species are paramagnetic. All odd electron plus 10 electron, 16 electron paramagnetic. All odd electron species. In addition to that, even electron species of 10 electron like boron, 16 electron like oxygen have paramagnetism because have unpaired electron. Others are diamagnetic. So this is a very important idea. Ready? Fine. And one more thing, that the bond order of CO3 plus that exceeds a value, unexpectedly the bond order of CO3 plus is found to be 3.5, not 3, which exceeds more than 3. Okay. So using this one, we can arrange some ideas, and I'll explain how we can show the molecular orbital diagram, and what about the shape of molecular orbital, and how we can predict the bond order using this trick, and moreover hydrogen bonding.